Good morning, everyone. My name is Jianxun Lian. I'm happy here to share our team's solution to the 2017 Recsys Challenge. I come from University of Science and Technology of China, and currently I am an intern at Microsoft Research Asia. This is the outline of my talk. First of all, I will give a brief overview of the task and our solution. Then I will introduce our three most important components with details. At last, I will draw some conclusions. The 2017 Recsys Challenge focuses on job recommendations on machine. Given a new job posting, we are asked to identify those users who may be interested in a job and who are also appropriate candidates for the job. The most interesting and exciting feature that attracts us to join this challenge is that, during the second stages, the recommendations submitted by participants will actually be rolled out in Shane's live system, which means that we can receive feedbacks and know the contribution of our model to the real users, not just some evaluation metrics on offline dataset like most of the other data mining competitions. For more details about this challenge, please refer to the official website. One big challenge is that we are facing the cold start problem. The items we are asked to give recommendations never appear in the past. So that the most popular recommender algorithms, such as collaborative filtering or matrix factorizations, are not suitable for this task. We use a content-based filtering method. Basically, we model the task as a binary classification problem, with positive label indicating the user is interested in the item. There are three core components in our solution. Firstly, we found that the selection of negative instance is notable. We propose a simple but effective algorithm to alleviate the discrepancy between the distribution of training and test sets. The second part is feature engineering. We extract comprehensive features from three pillars and verify their contribution to the final model. The third part is model selections. We choose the best model and as well the best parameters in order to achieve the optimal performance. Now let's move to the first part. Why do we need a negative sampling algorithm? Through the historical interaction logs, there are possible 6 types of activities. There is no doubt that we can use actions 1, 2, 3, and 5 as positive instance. And as a first choice, we usually use action 4 or some action 0s as negative instance. However, we found that this way does not work after we submit our initial results several times. It is not hard to understand the reason. Items appear in the interaction logs, which we use as the training sets. It is selected by Shane's own recommenders pipeline. So all items that are pushes to users are to some extent relevant to users. However, in a test set, there is no such a filtering layer, which means that items come from a totally open space without any prior information. Let's look at a quick example. Feature 8 shows the data distribution of training sets, and red points indicate the negative instance. As we prefer a classifier which produces bigger margins, we will choose classifier A's rather than B's as our discriminative hyperplanes. However, this training set is built after we applied a filter which removed many noise data points. In a test set, we do not have the filter at hand. Positive points and negative points are still distributed in the same way, but there are many noise data points around negative instance. In these situations, Plan B turned out to be a better classifier than Plan A. That's why we decide to construct a training set which simulates the distribution of test sets. The key point is to select negative instance. We call these steps as wide and deep negative sampling. That denotes the total user number as n, and total number of items is n. An instance is a user item pair. A naive method is to connect a user with all items. The disadvantages are obvious. The training file will be too large. At the same time, positive labels and negative labels are extremely imbalanced. So we propose the wide and deep negative sampling algorithms. In the wide part, we sample extensive items. But for each item, we only connect it with a small number of users. In the deep part, we sample a relatively small number of items. But for each item, we connect it with a lot of users. To evaluate the performance of different methods, we use the following 5 scores. The first 2 are rewards defined by the organizers. Since at the online stage, each target user can receive at most 1 recommended item. We follow this constraint to test the awards at top 1 prediction. We receive these 2 metrics by submitting a prediction file which covers 10% of the offline datasets. We also construct our local validation sets, and then the other 3 metrics are evaluated on our local validation sets. P at 1, P at 5 is the success user rates at top 1 and top 5 prediction, and AUC is commonly used for CTR prediction task. This table shows the results of different negative instance selection methods. The first row indicates we use users' negative activities as negative instance. We can see that it performed badly. We try to apply a simple filter on the test sets. We only consider those user item pair in which there is at least 1 common word from the user's profile and the item's profile. The performance is boosted around, but still not good enough. If we randomly sample some items as negative instance, the model performs good. We further add back the negative activities to this small random negative instance set. Surprisingly, the score drops. So we fully trust the power of random sampling of negative instance. Our proposed wide and deep sampling method performs best among different methods. We also demonstrate that either removing the wide part or removing the deep parts can cause performance decline. The second course component is feature engineering. We extract features from 3 pillars. The first pillar covers the similarities of the user's profile and the item's profile, including the document-to-document similarity, important attributes, metrics such as disciplines, industries, career level. We also intersect some users' attributes with items' attributes as categorical features, considering that using each base field separately may not be enough to explain the relationships. The second pillar covers the similarity between users' historical interest and the target item. we can regard that profile matching is the explicit message of similarities, and historical matching is implicit messages, which indirectly show user similarities with the item. Sometimes the user are not willing to input too much details in his profile, but his activities will not rise. And through the experiments, we found that historical matching is far more important than profile matching. The last pillar is bed of words. The first two pillars are relatively compact and dense features, and usually encoded as some similarity scores. In the third pillar, we use the raw words as sparse features. Since a user may contain many words in his profile and his historical interest items, these pillars of features make our training file pretty huge. For more details about the feature list, you can refer to we have open sourced our codes on GitHub. This table shows the contributions of different pillars of features. All indicates we use all the features, which leads to the best performance. The minus symbol means we remove this pillar from the entire feature set. We can observe that removing any one of the pillar will cause a drop in scores, especially when we remove the historical matching pillar. It indicates that users' interaction logs plays a key role in identifying his latent interest. And it is a pity that in historical matching pillar, at the first 2 weeks of online staging, our team did not include career levels and location similarity. Career level and location matches attributes. Because we thought career levels and location in users' profile is enough. However, it turns out that career level and location in users' historical clicked items represent the user better than what is in his own profile. This table lists the top 10 most important features from gradient boosting decision trees. Most of them come from the historical matching pillar. After the feature set is ready, we compare the performance of various machine learning models, including logistic regressions, support vector machines, factorization machines, gradient boosting decision trees, and also one pairwise ranking method, lambda mark. For each method, we tune its best parameter through a holdout validation set. And among these models, gradient boosting decision tree perform the best. One interesting observation is that GBDT has only a small improvement in AOC, but it has a great improvement in rewards at top 1 and success user rate at top 1. We also try to assemble several different models, which can lead to about 1.5% improvement. However, to keep our pipeline clean and light, we abandon the ensemble steps. We use only one GBDT model as our final model. Our wide and deep negative sampling will generate about 80 million candidates. If we include bed of words as features, the file size will exceed 4 terabytes. So we start seeing how to reduce the complexity of size. Usually, an online recommender system will contain a record layer, which can filter out most of irrelevant items for a user. Here we use a simple logistic regression model as a record layer. Firstly, we trained a logistic regression model based on the data from wide and deep sampling. Then we removed all instances that has a probability less than 0.01. Next, we trained a GBDT model on these filtered datasets as our final model. We can see that there is almost no performance drops after we use the logistic regression record layer, but the file size and running times greatly reduce. This is our ranking trends during online period. At the first 2 weeks, we use a weak model. And after we enable our fully automatic pipelines and add career levels and location features, our team remains the second place for the last 2 weeks. Up to now, we only use random samplings as negative instance. However, if we totally ignore the negative activities in the user's logs, we are surely losing some important preference information. So we hope we can use the negative activities as much as possible. We propose a new model which jointly learn to classify and rank. Through classifications, we hope to learn the relevance between the user and items. And through ranking, we hope to learn the user's preference. D plus is the positive instance, D minus is the negative instance, and R are sample from users' activity logs. We hope that the algorithm can assign a higher score for positive activities than negative activities. Currently, the model runs a little slowly, so we only do some experiments on a smaller validation set. This table shows that the new model improves a little. In this talk, I have shared our solution to the 2017 Recsys challenge. We have open sourced our code at GitHub. We introduced 3 core components of our solution, including negative sampling, feature engineering, and model selection. We also propose a new model which can jointly learn the relevance and preference. We will continue doing experiments with the new model, and maybe we can submit it to a journal. Thank you for listening. If you have any questions, feel free to contact me through email.